Good morning to all of my students. Myself, Mr. Dibyendu Mondal, Assistant Professor of Mechanical Engineering Department of Greater Kolkata College of Engineering and Management under JIS Group. In this pandemic situation, I am delivering my lecture through online mode and my video is uploaded in YouTube. Good morning. Today, I am discussing about thick spherical shell. Okay, thick spherical shell actually R2 this figure shows the spherical shell subjected to an internal fluid pressure P. R2 be the external radius and R1 be the internal radius. Consider an elemental disk of the spherical shell of thickness dx at a radius x. Let this elemental disk subtend an angle d theta at the center. Due to internal fluid pressure, let the radius x increase to x plus u and increase in thickness dx be du. Ey, that is the circumferential strain, and Ex, that is the radial strain, now increase in strain, that is equal to u. Therefore, final radius, that is equal to x plus u. Circumferential strain, so that is equal to Ey, final circumference, minus original circumference divided by original circumference. 2 pi x plus u minus 2 pi x divided by 2 pi x. So that is equal to u by x. Now original thickness of element, that is equal to dx, final thickness of element dx plus du. Radial strain, that is equal to Ex, final thickness of the element minus original thickness divided by original thickness. So dx plus du minus dx divided by dx, that is equal to du by dx. But from equation 1, u equal to x into Ey. Now radial strain Ex, that is equal to d by dx, x d dx x dot Ey equal to Ey plus x du Ey dx. Now consider an elemental spherical shell of radius x and thickness dx as shown in figure. Let px and px plus dpx be the radial pressure at radii x plus x and x plus dx respectively. Now sigma x is the circumferential tensile stress which is equal in all directions in a spherical shell. Considering the equilibrium of half of the elementary spherical shell on which the following external forces are acting: an upward force equal of pi x square px due to internal radial pressure. Here the diagram is given: spherical shell, half portion, one side internal pressure px, outside external px plus dpx. An upward force pi x square dot px due to internal radial pressure p. A downward force of pi x plus dx whole square dot px plus dpx due to radial pressure px plus dpx. A downward resisting force sigma x, that is equal to 2 pi x into dx. Equating the upward and downward forces, we get pi x square px equal to pi into x plus dx whole square dot px plus dpx plus 2 pi x dx dot sigma x. Pi into x square plus dx square plus 2x into dx px plus dpx plus 2 pi x dot dx dot sigma x. X square dot px, that is equal to x square plus dx square plus 2x dot dx, px plus dpx plus 2x dot dx dot sigma x. So x square dot px plus dx square dot px plus 2x dot dx dot px plus x square dpx. Okay, plus dx square dpx 2x dx dpx plus 2x dx sigma x. Neglecting squares and products of dx and dpx, we get x square dot dpx, that is equal to x square dot px plus 0 plus 2x dot dx dot px plus x square dot dpx plus 2x dot dx dot sigma x. So 0 equal to 2x dot dx dot px plus x square dot dpx 2x dot dx sigma x. Now 2 into sigma x, that is equal to minus 2 into px minus x into dpx by dx. Sigma x, that is equal to minus px minus x by 2 dpx by dx. Differentiating the above equation with respect to x, we get ddx of sigma x equal to ddx of minus px minus half ddx x dot dpx by dx, that is equal to minus dpx by dx minus half x dot d square px by dx square plus dpx by dx. At any point in the elementary spherical shell, there are three principal stresses. The radial pressure Px, which is compressive, circumferential or hoop stress sigma x, which is tensile, and circumferential sigma x, which is tensile of the same magnitude as of 2 and on a plane at right angles to the plane of sigma x. Now, radial strain if Ex, that is equal to Px by E plus sigma x by Me plus sigma x by Me. So Px by E plus 2 sigma x by Me. Now that is equal to minus Px by E plus 2 sigma x by Me tensile. Circumferential strain Ey, that is equal to sigma x by E minus sigma x by Me plus Px by Me. So 1 by E sigma x minus sigma x by M plus Px by M. 1 by E sigma x M minus 1 by M plus Px by M. Substituting the values of Ex and Ey from this equation minus Px by E plus 2 sigma x by Me, that is equal to 1 by E sigma x M minus 1 by M plus Px by M plus x dot ddx 1 by E sigma x M minus 1 by M plus Px by M. So that is equal to, you may write down, minus 1 by E within parenthesis Px plus 2 sigma x by M, that is equal to 1 by E sigma x M minus 1 by M plus Px by M plus x by E M minus 1 by M d sigma x by dx plus 1 by m dpx by dx. Therefore, minus px plus 2 sigma x by m, that is equal to sigma x m minus 1 by m plus px by m plus x m minus 1 by m d sigma x by dx plus x by m dpx by dx, or minus m px minus 2 sigma x, that is equal to m minus 1 into sigma x plus px plus x into m minus 1 d sigma x by dx plus x dpx by dx. So minus px m plus 1 minus sigma x 2 plus m minus 1 equal to x into m minus 1 d sigma x by dx plus x into dpx by dx. So minus m plus 1 px plus sigma x equal to x into m minus 1 d sigma x by dx plus x into dpx by dx. M plus 1 px plus sigma x plus x into m minus 1 d sigma x by dx plus x into dpx by dx equal to 0. Now substituting the value sigma x and ddx of sigma x from equation A, we get m plus 1 px plus minus px minus x by 2 dpx by dx plus x into m minus 1 into minus dpx by dx minus half x d square px divided by dx square plus dpx by dx plus x into dpx by dx equal to 0. Therefore, m plus 1 minus x by 2 dpx by dx plus x into m minus 1 minus 3 by 2 dpx by dx minus half into x d square px by dx square plus x into dpx by dx equal to 0. dpx by dx, that is equal to minus x by 2 m plus 1 minus 3x by 2 m minus 1 into plus x minus x square m minus 1 by 2 d square px by dx square. So x dot dpx by dx minus m minus 1 minus 3m plus 3 plus 2 by 2 minus x square by m into m minus 1 d square px by dx square equal to 0. Therefore, dpx by dx minus 4m plus 4 by 2 minus x by 2 m minus 1 d square px by dx square equal to 0. Therefore, minus 4 by 2 dpx by dx m minus 1 minus x by 2 m minus 1 d square px by dx square. তাহলে 4 dpx by dx plus x d square px by dx square equal to 0. Now substituting dpx by dx equal to z, dpx by dx equal to z in the above equation, we get 4z plus x dot d dx dpx by dx equal to 0. 4z plus x dz by dx equal to 0. So that is equal to 4z equal to minus x dz by dx. So dz by z equal to minus 4 dx by x. Integrating the above equation, we get log z, that is equal to minus 4 log x plus log c. Okay, log c. The above equation can be written as log z base e equal to log x to the power minus 4 base e plus log c1 base e, that is equal to log c1 base e into x to the power minus 4 log c1 by x to the power 4 base e So z equal to c1 by x to the power 4. But z equal to dpx by dx. dpx by dx, that is equal to c1 x to the power 4, or dpx c1 by x to the power 4 dx. Integrating the above equation, we get px equal to minus c1 by 3x cube plus c2. c2 is another constant of integration. Substituting these values of px in equation A, we get sigma x equal to minus c1 by 3x cube plus c2 minus x by 2 dpx by dx. So c1 by 3x cube minus c2 minus x by 2 c1 by x to the power 4. So that is equal to c1 by 3x cube minus c2 minus c1 by 2x cube, that is equal to minus c1 by 6x cube minus c2. If we substitute c1 is equal to minus 6b, c2 is equal to minus a in equation, we get px equal to minus 6b by 3x cube plus minus a 2b by x cube minus a. Sigma x equal to minus 6b by x cube minus a equal to b by x cube plus a. The constant a and b are obtained from initial given condition. For example, at x equal to r1, px equal to 0, at x equal to r2, px equal to p. So substituting the value 0 equal to 2b r1 cube minus a and p equal to 2b r2 cube minus a. Now solving the equation A, after solving you get A equal to p r2 cube divided by r1 cube minus r2 cube, and b equal to p r1 cube r2 cube divided by 2 r1 cube minus r2 cube. A thick spherical shell of 200 mm internal diameter is subjected to an internal fluid pressure of 7 Newton per millimeter square if the permissible tensile stress in the shell material is 8 Newton per millimeter square. Find the thickness of the shell. Here internal diameter 200 mm, internal radius 100 mm, internal fluid pressure P equal to 7 Newton per millimeter square, permissible tensile stress sigma x equal to 8 Newton per millimeter square. The radial pressure and the hoop stress at any radius of spherical shell are given by Px equal to 2b by x cube minus a, sigma x equal to b by x cube plus a. The hoop stress sigma x will be maximum at the internal radius. Hence, permissible tensile stress at 8 Newton per millimeter cube is the hoop stress at the internal radius. At x equal to 100, px equal to 7, so 7 equal to 2b by 100 cube minus a. So that is equal to, and x is equal to 8 is equal to b by 100 cube plus a. Substituting these values in equation, and after calculating we get outside pressure px equal to 0, okay, and substituting the value v in equation 4, 8 is equal to, okay, this by this plus a, 5 plus a, okay. So substituting this value, you calculate r1 equal to r1 cube equal to 1000 by 3. So r1 is equal to 10 to the power 7 by 3, 1/3. So that is equal to 3.33 3 1/3 10 square 149.3. Therefore, thickness of the shell, that is equal to R2 minus R1. 149.3 minus 100, so 49.3 millimeter. Okay, thank you. Last, if you like my video, you have to subscribe. Okay, thank you.